Hello BC kids, we are looking at section 9.2 today with second derivatives of parametric equations. And so here's the interesting notation for second derivatives. You haven't seen this for a while, but it should kind of ring a bell. It's d squared y over dx squared. That's the notation for a second derivative. I'll give you a little note about that right here. Notation for the second derivative. In case you haven't seen it for a while and you forget, if you've got a 3 there, it's a third derivative, yada yada down the line. Okay, so here's what you need to do to find the second derivative of a parametric function. It's going to be the derivative of, actually it's just a d over dx, if I use the right notation here, d over dx of dy over dx. Which means it is d over, I'm going to give you all the fancy pants thing, and I'm going to shorten it up for you. D over dt, because now we're parametric, right? We're not just y's and x's. D over dt, derivative of dy over dx over dx over dt. All right, so here's ultimately what we're going to get to. Equals, I'll put it in red. Dy over dx, take the derivative, and divide it by x prime of t, the derivative of the x parametric equation. You remember last section, we talked about how to find dy over dx. So it's dy over dt divided by dx over dt, and then that's divided by dx over dt. It's kind of like a complex fraction in a sense. So really this whole thing is, given the following parametric equations, find the second derivative in terms of t. Then they're going to get into talking about what does second derivative have to do with graphs and such. And you know second derivative has to do with the concavity of the function. So they're going to pull in concavity and such as we go along. But for now, first couple examples, they just want to talk about what would the second derivative be in terms of t. All right, so let's see if we can apply this. We need to know what dy over dx is first. So this is what we did in the last section. We're not going to do anything new yet. So just do the same thing you did in the last section. You take the derivative of the y, divide it by the derivative of the x. Now these are not in pretty notations right now. This one is like x of t is t to the 1/2, and y of t, notice I haven't derivatives yet, I'm just looking at setting it up so I can, is 1/2 t squared, and then minus 1. 2 times 1/2 is 1. That's what I want a derivative. So all right, let's go over here, my y function, let's take the derivative. 2 comes down in front, 2 times 1/2 knock each other out, so I just have a t. That was nice. Derivative of 1 is 0, so that's it. Come over here to my derivative here, now the 1/2 comes down in front, t to negative 1/2, 1 less power. This becomes, if I think about this, 1 divided by 1/2. If you have to, go over to the margin here. 1 divided by 1/2 is the same thing as 1 times 2 over 1. So it's really a 2. I just took my coefficients. Now let's talk about the t. T has a power of 1. We saw this in the last video. 1 minus a negative 1/2 is 3/2, 1.5. So 2t to the 3/2, that's what dy over dx equals. That's my first derivative, right? So my first derivative is 2t to the 3/2. Now let's go for the second derivative. Here's my notation, d squared y dx squared. Now here's what I've got to do. I've got to take the derivative of that. The derivative of my first derivative, dy over dx. Derivative of this, let's just start with that. So it's 3/2 comes down and multiplies by 2. That gives me a 3. Got to take t to 1 less power. 3/2 minus 1, or minus 2 over 2, is 1/2. over. Now I've got to take the derivative of the x. Well, the derivative of the x was what I just figured out over here. It's that denominator that I had up at the top. So this is 1/2 t to the negative 1/2. So you already calculated that. You don't have to redo that. All right, let's try this again. If I go 3 divided by 1/2, 3 divided by 1/2, that's 3 times 2 over 1, that's 6. If I have 1/2 minus a negative 1/2, that gives me 1, so this is just a t. And that is my second derivative. There's a lot of playing with fractions and such in these. You got to just kind of remember it. If you need to go off to the margin and do your work, that's okay. If you can do it in your head, that's cool too. All right, number 2, find the second derivative. There's nothing I need to do to these equations to make them better to derivative. So here I go. If I find dy over dx, derivative of 4 sine of t is 4 cosine of t. Derivative of 3 cosine of t is negative sine, so negative 3 sine of t. Now you're going to see that they use a whole lot of trig identities in these problems, because if I think about, and the reason why, you'll see, if I go to take, this is a perfectly fine derivative, the way that it is. But if I have to take a second derivative of that, I'm going to have to quotient rule it. But there's a way to avoid that. So they try to use the trig identities so that you don't have to get too terribly cumbersome in these things. So if I think about this, cosine over sine is one of the quotient rules of identities. So you'd have 4 over negative 3, negative 4/3. Cosine over sine is cotangent of t. And you see how that eliminated me to have to use the quotient rule on this thing. So if I do that, here comes my second derivative. So there's my first derivative. Here comes the second. I take the derivative of this, negative 4/3. Derivative of cotangent, oh, do you remember? Do you remember? It's a negative cosecant squared. Over the derivative of x. Well, that's this guy here, the same denominator I had from up above. So here's the first thing that I notice about this whole hot mess. I notice that I have a negative and a negative, makes that positive, but that positive is being divided by this negative, so ultimately I'm going to have a negative answer. What is 4/3 divided by 3? Actually, maybe this one I want to do a little differently. Let me do it. I'm going to say negative 4/3 gives me a negative. I'm going to keep it at, actually, I'm just going to take the numerator first. Negative, negative is positive. I have a positive 4/3 cosecant squared t. And I'm dividing that by, and remember, keep, change, flip. I'm going to have to flip this. So ultimately I'm going to multiply it by 1 over a negative 3 sine of t. I'm just separating the complex fraction. So I made it negative 4/3 times a negative cosecant squared is a positive 4/3 cosecant squared. And this guy is divided by a negative 3 sine of t, which means it's multiplied by 1 over that. That's where I'm at. Now I've got the cosecant. Well, I can go 2 different ways. These are a lot of times, you know how you have equivalent forms on like the multiple choice? There's a lot of different ways you could write the answer to this. But let me say we know that 1 over sine over here is the same thing as a cosecant. So what I really have is 4/3 cosecant squared t times a negative 1/3. 1 over sine is cosecant of t. So ultimately I have a cube of that thing, and I have negative 4/9. Negative 4 over 9 cosecant cubed t. That's my final best answer. Could I have written that in terms of sine? Sure, you could have. You would have had negative 4 over 9 sine cubed t, and that would be an equivalent form as well. All right, there you go, one with a trig function. Now let's take some concavity and put that into this whole mixture since we're talking second derivatives. And here's what that looks like, number 3. At t equals 1, find the concavity of the graph defined parametrically with x is t cubed plus 1 and y is t to the 4th plus 1. So in order to get to the concavity, I need to get to the second derivative, and so that's what I'm going to do. So the question's really the same as what I've been doing. Take the first derivative, dy over dx. That's going to be my y equation, 4t cubed plus 1, over the derivative of my x, 3t squared, now realize I'm going to have to take the derivative of that. So right now it's in a Hody high form. I've got to use quotient rule. But maybe I can rewrite it a little differently so that I can not have to get into all that. Is it wrong to go quotient ruling? Absolutely not. We'll get the same answer in the end. But I could also, because this is a monomial denominator, I can split it. It'd be like 4t cubed over 3t squared plus 1 over 3t squared. And that becomes a 4/3 t. 3 minus 2 is 1. And this would be like plus a 1/3 t to the negative 2. And so if I put it in that kind of a form, that it makes it easier for me to use the power rule on it to take the derivative for the next part. Second derivative. Take the derivative of this. Well, the derivative of 4/3 t is 4/3 plus the derivative of this is negative 2/3 t to the negative 3. And all of that is over my dx here, which is 3t squared. And you say, man, that looks like a hot mess. And I say, yeah, it does. But they want me to evaluate it when t equals 1. So at this point, I really can put that in there and figure out what that would look like. So if I put the 1 in, I have 4/3 plus, actually minus, right? 2/3. Because of that negative. And then it's t to the negative 3, meaning 1 over 1 cubed, right? Divided by 3 times 1 squared. I have 4/3 minus 2/3 over 3, or 2/3 over 3, or 2/3, can you still see me now? I lost you. Hold on. Now I'm found. 2/3 divided by 3. I'm going to take you the long road. You can probably figure this out from here. 2/3 times 1 over 3, which means I get 2/9. And it's saying to me, find the concavity. And you said, yeah, it's 2/9. What does that mean? It's positive. So I know it is concave up because the second derivative is positive, is greater than 0. All right, that's the end of the examples for this particular section. That's it. It's just finding the second derivative and then applying it in concavity kind of situations. All right, a couple questions I'm going to do with you. I picked a few. The first one is number 4 that I picked. And the question says, given the following parametric equations, find the second derivative in terms of t. Okay, well, we did that. What I find interesting about this one versus the others, see, this is an x of t, this is an x of t equals, yeah, now it's dx. What did they give you? They actually gave you the derivative, the first derivative. So this is sweet. I don't know that you would have caught that they gave you half the problem. dy over dx is, here's the derivative of y, the sine of t squared. Here's the derivative of x, 4. And you say, okay, cool, that's it. Half my work is done now. Let's go for the second derivative, which is what they're asking for. Derivative of this. Now this would be the same thing as 1/4 the sine of t squared. Just if you think of it that way, that's going to make your life a little bit better. So I would have 1/4 the cosine of t squared times the derivative of t squared, which is 2t, over the derivative of x, which is 4. So let's see if we can clean it up and figure out what the final best answer is. This one would be 2t over 4, so it would be, I'll come down here, 1/2, 2 over 4, 1/2, t cosine of t squared, and that's being divided by 4, so divided by 4 is times 1 over 4, put it together, and I get 1/8, 2 times 4 is 8, t cosine of t squared. And there it is. So this one was different because they actually gave you the derivatives. It makes the problem half as bad. All right. Next one I picked was number 5. With this, because see how you're going to product rule this part? That gets a little messy. So because of that, that's why I chose this particular one. Let's see if we can do it. We've got, now we're back to x equals and y equals, so we're not given the derivatives like we were back in number 4. So this is number 5 that we're looking at. And I have my dy over dx I'm working on first. I can't get to the second derivative without going through the first. So here it is, derivative of y. Well, here's your product rule on this one. You've got the first t times the derivative of the second. E to the negative t is e to the negative t times the negative 1. So negative e to the negative t plus the second e to the negative t times the derivative of the first, which is 1. Okay, there's your derivative of y. We'll clean it up in the next step here. And the derivative of e to the t is just e to the t. All right, so let's see what we got. We've got a negative t, e to the negative t, plus e to the negative t, all over e to the t. Can we make that better? And the answer is yes. Let's think about this for a second. If I factor out, I'm going to come up above, if I factor out an e to the negative t from this numerator, e to the negative t, both of them have it, that's going to leave me with a negative t plus 1. Then I have identical things on the top and the bottom, so I can combine them together to become one unit. E to the negative t over e to the t is going to be e. What do you do with the exponents? You subtract them. Negative t minus t is a negative 2t. And then I'm still left with my parentheses here, but normally they're written the other way around with the 1 minus t. 1 minus. It's a positive 1, it's a negative t. All right, there's my official first derivative. I'm going for the second derivative. Couple options on this. Could I distribute this through? Sure I could, but then I'd have to product rule this. And I guess either way I'm going to have to product rule. So I'm going to leave it the way it is. This is my first term, e to the negative 2t. Second term is 1 minus t, and I'm going to product rule those two pieces for my second derivative. D squared y dx squared. All right, so first e to the negative 2t times the derivative of the second. Well, the derivative in here is a negative 1 plus the second 1 minus t times the derivative of the first. Derivative of the first is a negative 2 e to the negative 2t. That's all my first derivative, and all of that is over my derivative of x, which is e to the t. And then my task is to try to clean this thing up. So let's see what we got. I'm going to keep going to the right. I have a negative e to the negative 2t. That's this whole first term. I have over here want to keep it, it's going to be minus because of negative here, minus 2e to the negative 2t times 1 minus t. And all of that is over in e to the t. Now from these two terms, they both have an e to the negative 2t. That means I can factor it out. This is going to get kind of crazy. So if I factor out just the e to the negative 2t, e to the negative 2t, on the top, that's going to leave me with a negative 1. It's going to leave me with a negative 2 times 1 minus t. And all of that is over e to the t. So I factored it out here, negative 1. Factored it out here, negative 2. But I still have this craziness at the end. Now the reason why I did that is because now I can create not two fractions, a single fraction. E to the negative 2t minus this t, they're both e's, gives me e negative 2t minus t is negative 3t. And then I'm left with, that takes care of all this, I have a negative 1, I'll go up above, negative 2, and I have a positive 2t. Negative 1, distribute the negative 2 plus 2t gives me this. So I end up with a negative 3 plus 2t. That's my final answer. How about that crazy algebra? Lots of work with powers and such, and remembering your rules for how they go. All right, close to done. Number 8 is next on my list. Here comes number 8. It says, here's your x equation, here's your y equation. Find the slope and the concavity at pi over 6. We love our trig functions. This one writes small because it goes quite a ways. All right, I have, I'm going to find my first derivative first to find the slope. Second derivative is going to talk about concavity. So I need both derivatives. You can't get to the second derivative anyway unless you go through the first, so you got to do the first as it is. dy over dx. Derivative of y. Well, derivative of 1 is 0, and the derivative of tangent is secant squared. So this guy's going to be 2 secant squared theta. All right, derivative of x. Derivative of 2 is 0. Derivative of secant is secant tangent. All right, thank God they gave you an angle. It's just an x or a theta, so that you don't have to chain rule. So here's what I have. So you can cancel a secant, right? So I have 2, I still have a secant up top, and I have a tangent on the bottom. Could I leave it like that? Sure, I could. But I could also say 2 secant is 1 over cosine. Tangent is sine. Actually, tangent is, hang on a minute, let me do it this way so I don't confuse you. Divided by tangent, which is sine over cosine. So what I really have is 2 over, 2 times 1 is 2, over cosine of theta times, remember I keep change flip, so I'm dividing by sine over cosine means that I'm multiplying by cosine over sine, which makes me do a happy dance because my cosines are out, and here I am, 2 over sine of theta. That's the best I've got for the first derivative, but now they want me to evaluate it when the theta is pi over 6. So I've got to go to think about my unit circle, right? And thinking about my unit circle, what's the coordinate at pi over 6? I'm going to come over here. Pi over 6 is the first one you come to. It is the square root of 3 over 2, 1/2. Pi over 6. So the sine is 1/2. So that means for our case at pi over 6, I get 2 over 1/2. 2 divided by 1/2 gives me an answer of 4. That's my slope. That's the first derivative. All right, let's go for the second derivative so I can talk about the concavity. A couple different ways that I could do this. I guess that I could say 2 over the sine. Well, isn't 2 over the sine the same thing as 2 cosecant of theta? That's a dx there. 2 cosecant. Could I say that? Maybe does that make me any better? So I take 2 cosecant and I want to take the derivative of that. So if I do cosecant, it is, let's see. I did this a totally different way when I was doing it on my notes. So secant cosecant is negative cosecant cotangent, right? Yikes, trig rules. All right, pause. Where's my trig rules? Did I say it? I went back, gosh, how did I do this? When I would probably pursue, now I don't remember, I don't want to do this incorrectly on here, but you can go back and use your trig rules for cosecant. I don't remember derivative of cosecant. I should know that off the top of my head. But anyway, here's where I went so I can take you on a road that's going to be clear. I went back and did the original here. I took the original, this guy. And I said, okay, well, if I am a 2 secant squared, what did I do? Cosecant cotangent. Maybe I did take it here. It's negative cosecant cotangent. So negative 2 cosecant cotangent is my first derivative. The derivative of this would be negative 2 cosecant cotangent. So it is cosecant cotangent. And then I took and divided it by my secant tangent. That's exactly where I'm at. So anyway, back over here, I did change it to this, and then the derivative of cosecant is negative cosecant cotangent. So that's good. Then I'm going to take this thing and I'm going to keep change flip it. So I get negative 2, and as I do this, I'm going to change these into sines and cosines. So I'm in the numerator. Cosecant is 1 over sine. Cotangent is cosine over sine. And I'm dividing that by secant. Maybe I should parenthesis it. I'm dividing by secant 1 over cosine times tangent, which is sine over cosine. So let's see if I can make this any better. Put this together as 1, negative 2 cosine of theta over sine squared theta times, remember keep change flip, cosine of squared theta over sine of theta. And that gives me, believe it or not, negative 2 cosine cubed theta over sine cubed theta. You could, again, equivalent forms. You could put this as, well, let's leave it there because it's going to be easier when we plug in our values. You could change this to cotangent cubed. But then you've got to do all your algebra to figure out what cotangent would equal from pi over 6. So right now, if it's in sines and cosines, I'll know from my x's and y's. All right, so negative 2. Cosine is the x value. Square root of 3 over 2 cubed. Sine is the y value, 1 over 2 cubed. All right, let's see if we can work out the details on this. I'm going to come down into the box below just so I have some space. This would be negative 2. If I cube this square root of 3, I get 3 square root of 3. Because remember, I'd have 3 square roots. Square root of 3 times the square root of 3 would be 3, but I still have 1 inside, so that's this guy. And on the bottom, oh, actually, wait a minute. Forgot my bottom. Forgot the denominator on this guy. If I cube a 2, I get an 8. That's these two pieces. And then that's being divided by 1/8. Right? 1 cubed, 2 cubed. So I really have negative 6 square roots of 3 over 8 times 8 over 1. 8's cancel. I get a negative 6 square root of 3. And the question is, oh my gosh, we lost the question, right? What's the concavity at pi over 6? Well, at pi over 6, when I plugged it in, I get a negative value. That means it's concave down at pi over 6 because the second derivative is less than 0. It's negative. All right, kids, that's going to take care of section 9.2, and I will see you in class. Shoot me an email if you have questions. Bye.